Welcome back. So let's continue talking about rational functions, specifically focusing on their asymptotes, the vertical asymptotes, horizontal asymptotes, and we can also talk about the end behavior. When we talk about the horizontal asymptotes, we're really talking about the end behavior. As x has become infinitely large or as x has become infinitely small, what is the function doing? And as we'll see, there's three different possibilities. Something you saw in college algebra, but it was very confusing, very difficult in college algebra, and hopefully we'll clear things up here a little bit. So let's take a look at just kind of the general rules and properties. So a little bit of writing here, a little bit of notes. So I want to look at the asymptotes of rational functions. And remember, a rational function is defined as some p of x over some h of x. And remember we said this is a sub n x to the n plus everything else all over b sub m x to the m plus everything else there. And of course, in the end, a sub 0 plus b sub 0. I think we should probably already know the significance of the constants here when it comes to this. Doesn't have anything to do with the asymptotes, but is an important characteristics. All right, so let's take a look at all the different properties here. First, the vertical asymptotes. The vertical asymptotes are the zeros of h of x, the denominator. So I'm going to set h of x equal to 0 and solve. And anything that makes the denominator become 0 is a vertical asymptote, a domain restriction, a do not cross line. Those are my vertical asymptotes. The horizontal asymptotes are going to be, also think about these as the end behavior. And it all depends on the degree of the numerator and the degree of the denominator. So remember, n is the degree of the numerator, m is the degree of the denominator. And I have three possibilities here for the end behavior. And when we talk about the horizontal asymptotes, we're really talking about what is f of x doing when x becomes infinitely large. So as x is increased without bound, what's the function doing? Is it increasing without bound? Is it approaching a number? What number? Or is it just going to 0? So the three possibilities here. So let's take a look at all three possibilities. In the first possibility, the degree of the numerator, it could be less than the degree of the numerator. The top is smaller than the bottom. Well, if that's the case, then the horizontal asymptote is the line y equals 0. Just like in our parent function, 1 over x. Think about 1 over x. The function as it increases without bound or decreases without bound approaches 0, or 1 over x squared. The numerator, the degree of the numerator is less than the degree of the denominator, then it approaches 0. The second possibility is that the degree of the numerator is the same as the degree of the denominator. Well, if that's the case, then the horizontal asymptote is y equals the lead coefficient over the lead coefficient. And that's a line. Remember, these are numbers. These are going to be constants here. So it's the lead y equals whatever that is over whatever that is. The lead coefficient over the lead coefficient. Okay. And of course, the third possibility, and this is the one that these you probably spent a lot of time with in college algebra, but the third possibility is where it kind of gets messy. And in the third possibility is where the degree of the numerator is greater than the degree of the denominator. Now, if that happens, strictly speaking, we don't have a horizontal asymptote. It's going to be some sort of slant or oblique asymptote. Not a nice, well-behaved horizontal line. Not a y equals k, a constant. It's going to be something else is going on. And how do we find that function? Well, the asymptote, the oblique asymptote, is going to be y equals some q of x. And how do we find q of x? Well, we take the p of x, divide it by the h of the x, and we're going to get a quotient and a remainder. And we're going to ignore the remainder here. The line q of x is going to be the slant asymptote after long division. And this can be a little bit awkward. We're going to look at an example of this. This can be a little bit frustrating here. I'm going to look at an example of this. All right, so in the first two cases, I think it's pretty obvious. If n is less than m, it's going to go to 0 if they're the same lead coefficient over lead coefficient. I don't think those will give you a hard time. So let's take a look at this one, the one that's a little bit more difficult. Suppose I have the following function. F of x equals x cubed over x squared minus 9. All right, so the things that should jump out at me as soon as I look at this is that I have a domain restriction here. X cannot equal negative 3 or 3. As a matter of fact, x equals negative 3 and x equals 3 are my vertical asymptotes, 3 and negative 3. When x is 0, well, am I allowed to plug in 0 here? If I plug in 0 for x, I get 0 over negative 9, which is 0 for y. This is going to go through the origin. It goes through the origin. I've got these two asymptotes, so as x is approached negative 3 or 3, it's either going to go to infinity or negative infinity. The value of the function will increase without bound or decrease without bound. But what about that horizontal asymptote? Let's find the horizontal asymptote. And as we look at this, we're going to discover that it doesn't actually technically have one. There is no k value because the degree of the numerator is bigger than the denominator. So this is not going to approach some nice number. If the x squared minus 9 was in the top and the x cubed was in the bottom, if it was upside down, then it would be approaching 0 because the numerator would be less than the denominator. Or if this was a nice squared here, x squared over x squared minus 9, then it would be y equals 1, lead coefficient over lead coefficient, 1 over 1. But in order to find the asymptote here, we're actually going to have to do long division. I know some of you are thinking, well, couldn't we do synthetic division? No, because that's quadratic. You can only ever do synthetic division if you've got a linear denominator. So I'm actually going to have to do long division here. What's it going to look like? I'm going to have the x squared minus 9, and I'm going to have x cubed plus no x squareds plus no x's plus nothing. And I'm really interested in this quotient. I'm going to have a remainder. It's not going to go in evenly, but I'm interested in the quotient, the part that's going to be up here. All right, so here we go. What times x is going to give me x cubed? Well, x. So I'm going to put x here. X times x squared gives me x cubed. It also gives me negative 9x. And then I subtract. X cubed, take away x cubed, nothing. No x squareds. No x's minus negative 9x's. 0 minus negative 9 is 9x. Bring down the 0. What times x squared is 9x? Well, nothing here. There is nothing here. So that's going to end up being my remainder plus 9x over x squared minus 9. There's my remainder. That's the line I'm interested in. So I have an oblique or slanted asymptote at the line y equals x. Let's take a closer look at what this looks like. Take out your calculators. I'm going to clear out the stuff that was in there from before. First, I'm going to graph this rational function right here. So it's going to be x to the third power divided by, make sure we get that in parentheses, open parentheses, x squared minus 9, close parentheses. Standard viewing window here, zoom 6, standard viewing window. And we can see that the negative 3 and the positive 3, we can see my horizontal asymptotes in there, 3 and negative 3. I'm going to zoom out a little bit on this because I want to take a look at this, the behavior here. So I'm going to go to my window, leave the 10s from negative 10 to 10, but the y's I'm going to make them from negative 20 to positive 20. And I'll scale them in 5 so that it's not too crazy on the scale. There we go. That's a little bit nicer. I can take a look at what's going on here. Now it's the scale. Remember, this is going from negative 20 to 20. That represents a range of 40 units right there, where this only represents 20 units. So it's not all nice and squared up. But I can see that my asymptotes here, my end behavior, as x is increased without bound, it's not going to a nice number. That's going to just keep going, getting bigger and bigger and bigger. As x is decreased without bound, it's getting smaller and smaller and smaller. We have this end behavior asymptote over here. Let's graph it on top of this. So I'm going to go to my y equals, graph the line y equals x, and graph it on top. And there it is, the slant asymptote. I'm getting closer and closer and closer to it. I'm getting closer and closer and closer going this way. The line y equals x. And the slant or oblique asymptote could be a quadratic or a cubic. If this had been a fifth degree over a second degree, fifth degree over second degree would have given me a cubic end behavior. In some ways, we can say that as x is increased without bound, y is increased without bound. The function increases without bound. As x is decreased without bound, the function is going to decrease without bound. And that's true. But it's increasing or decreasing at a very specific rate according to this oblique or slant asymptote. All right, let's take a look at an application problem with specifically dealing with horizontal asymptotes. The classic problem that deals with horizontal asymptotes is a concentration problem. And this is one of the big problems on the final exam too, a concentration problem here. So suppose I have 50 liters of 35% acid mixture. So I've got 50 liters of an acid mixture that's 35% acid. Now I want to get, I want to make this a lot stronger. So I'm going to say, well, how many liters of pure acid? Now pure acid is going to be 100%. How many liters of pure acid must be added to create a mixture of 75% strength? All right, so this is a concentration problem. Concentration. And if I just think about it as numbers, think about it like that, or just as words. Concentration equals the amount of acid over the total amount of the mixture. Let's get a little bit more specific now. So my concentration, I'm going to say, let's let x equal the amount in liters of pure acid that needs to be added. So my concentration as a function of x is going to be, well, how much acid is in there already? Well, I've got 50 liters of 35%. So 50 liters of 35%. Whatever 35% of the 50 liters is, that's pure acid. And I'm adding X number of liters, that is 100% acid, divided by, now how much of the mixture is in there? Well, I'm starting with 50 liters and I'm adding X liters. So let me pause here for a moment and kind of break down this concentration problem. The amount of the acid that's in there already. There's 50 liters in there, but only 35% of it is acid, and I'm adding X liters, that is 100% acid, pure acid, over the amount of the mixture is 50 liters plus X liters that are being added. So this is the strength and this is the amount. Strength over amount gives you the concentration. If I was adding pure water, by the way, this would be 0% acid, and I would be diluting the mixture. And I might say, well, how much pure water is needed to dilute the mixture to 25%? So then I would have 50 plus X, I'd have, this would disappear because it would be 0%. But here I'm adding to strengthen it, to increase the concentration of the mixture. So there's my formula. So now let's take a look at this, kind of put it all together and solve. So what I need to solve, let me rewrite the formula down. My concentration as a function of the amount of pure acid I'm going to add is 50 times 0.35 plus X times 1.00 over 50 plus X. And I want the concentration to grow to 75%. So the concentration, I'm going to put 75% in here. So 0.75 equals 50 times 0.35 plus X times 1.00 all over 50 plus X. And of course, I can do this in the calculator nice and quick and easy. This is just going to be X. If I take a look at a simplified version of this, 50 times 0.35, it's really going to be solving this. 0.75 equals 17.5 plus X over 50 plus X. And this one would be easy to solve algebraically. Cross multiply. 0.75 times this equals that. Distribute. Combine like terms. This would be very easy to do algebraically. I want to take a look at it on the calculator so I can talk about concentration. So in Y1, let's clear out the stuff that's in there from before. I'm going to put my concentration formula. Open parentheses, 17.5 plus X, close parentheses, divided by, open parentheses, 50 plus X, close parentheses. That's my concentration. Now my concentration is going to go from 0% to 100%. So as I go to my window, I'm going to change my window here. My X's represent the amount of acid that I'm adding. Well, I don't know. I'm going to go from 0 to maybe 100 liters of acid, scaled in maybe 10-liter increments. The Y's represent the strength. This represents the concentration. Well, I could have 0% concentration, which would be no acid at all, and 1.00, which would be 100% concentration, and I'm going to scale it in 10% increments. So I'm going to go from 0 to 1 here. And then as I graph it, here is my concentration. It's starting at 35% strength. That's 0.35 there, 35%, and it's getting stronger and stronger and stronger and stronger and stronger and stronger. I want to know when it reaches 75%, so I'm going to go back to Y2. I'm going to put in 0.75, 75% strength, and graph it. And right there at that point of intersection, so I'm going to go to second trace, calculate button, Casio users, GSolve, intersect, calculate the intersect. And it looks like when X is equal to 80. And if you solve this algebraically, cross multiply and solve, you would get 80 as well. So now I'm going to answer my question. How much pure acid do I need to add? 80 liters. And then the concentration will be up to 75%. All right, so go ahead and stop the video now and you can work on the homework. Remember, all these videos are available on YouTube. You can go watch them and play them back and pause them if you need to look at it again. All right, good luck, guys. Talk to you tomorrow.